Yes, welcome to this introduction to Medini Analyze, our functional safety solution for the automotive, avionics, and industrial domains. My name is Olaf Kart. I am the product line director for Medini, part of ANSYS Medini Technologies AG. In ANSYS, we basically support a number of digital safety and system simulation capabilities and tools starting from systems engineering and systems modeling with our Scaled Architect offering, over embedded software development solutions, model-driven solutions based on Scaled Suite and Scaled Display. We do support system simulation and digital twin development, basically taking into account multi-physics simulation at system level in real time, and the detailed physics simulation actually is supported by a number of very specialized tools for the domains like radar, waves, fluid, mechanical, and so forth. Um, and the fifth and the core for this presentation will be our functional safety analysis solution called Medini Analyze. So we are looking into the implementation of functional safety standards. We do this for different industrial domains like automotive, avionics, as you see here. Um, Basically, the functional safety standards require us to implement a number of safety analysis methods in a highly integrated, in a consistent and thorough manner. So the methods that we are talking about here are not really new. So they are well matured over decades, right? Um, we talk about methods to do a very early hazard analysis and risk assessment, the HARA in the automotive domain or FHA in avionics. We talk about establishing safety goals and refining safety goals into safety requirements. We talk about creating functional and technical safety concepts, which basically summarize the idea and the approaches to safety in a concept, right? These concepts are supported by safety architectures and safety mechanism designs, which we are doing in a very detailed, right? And then we have a variety of analysis methods, each of these actually focusing on a specific aspect of our system. So we talk about methods like FMEA, FMECA, FMEDA, for example. For the hardware safety analysis, we talk about diagnostic coverage metrics, FMEDA again, or single point fault, latent fault, diagnostic coverage metrics for the automotive domain. At system software safety analysis, we also, in many cases, take into account fault tree analysis, or FTA. And obviously, we have to care about common causes and um, other kinds of cascading failures, for which a method called dependent failure analysis turns out to be very helpful. So again, none of these methods is really new, so they are all in place for many, many years, right? But the requirement here to actually have all these methods integrated with each other and working together towards the ultimate goal of a functionally safe product, that remains a challenge, right? In many situations, we have seen that companies are implementing this in different tools. These different tools are very tough to get consistent with each other. It's a very time-consuming task, and it also can become very complex because each single tool that is added to this, let's call it zoo, right, will basically imply a number of additional challenges. So here we have one example from Audi published on our user conference, where this is basically also the starting situation for them, using different tools for the different analysis techniques and for the different architectural uh, modeling work that is being done. And it's really, really tough to get those consistent, traceable, and yeah, in the end, integrated. With Medini, we follow a little different approach. In the core of our solution, we have system models, and these models actually describe a system at different technical abstraction levels, right? So it can start at really functional level where we actually have only a set of functions. We talk about malfunction of these functions. We talk about relations between functions, right? Then it can also go down to a more detailed level of architectures at system level, at hardware, at software level. We talk about detailed software and hardware design, and we even can talk about using models at for IP design and other semiconductor-related tasks. We extend these models with properties which are relevant for safety analysis, right? These can be, for example, failure modes, failure rates, failure rate distributions, um, SIL, RSIL related properties, can be allocations of requirements to elements in our system models. So these kind of parts of a failure model that are also in the end part of the system models themselves. So we keep all this information in one place, which are our system models. Now, what we do then is for the different safety analysis methods, we connect the detailed methods, right, directly to the system models, right? So we have only one source of data for the safety analysis, which is then carried out in these different analysis tools, right, or methods, right? So for example, here we have an FMEA. An FMEA is nothing else than the presentation of the content of the system models in a different layout, in different notation, right? In FMEA notation. Can be supported by a failure net, obviously. Same thing for fault trees, for example. An event in a fault tree here can represent an element from our model, right? So we keep that traceability between events in the fault tree, as an example, and the elements in our system model. Same holds for FMEDA or for the hardware-related safety analysis methods. Um, they also connect to the elements of the model at the relevant technical abstraction level, right? Um, we can use failure rate prediction handbooks in order to establish additional properties for our system models at electronic component level, right? We can add and maintain safety requirements and their allocation to elements of the system model. And finally, of course, the HERA or the PHA or FHA is obviously also connected with their safety objectives and safety goals and malfunction analysis and so forth, connected to these elements in the system models. So these models are really a core in Medini Analyze, and this approach actually ensures a very high level of consistency. It ensures traceability, and also it allows for a very efficient safety analysis workflow. Few words again about these models and the role of the models, right? So on the left-hand side, you see a very abstract model of a vehicle function, really at a very early stage, at a conceptual stage, right? So only very few definitions and elements are in the model. It's a basic view of how a vehicle level function should look like, how it should behave, right? We refine this kind of model into a technical view, a technical safety architecture model, okay, where we then really talk about technical components. We talk about CAN transceiver for CAN communication. We talk about micros and three-layer architectures, and we talk about power supply and according monitors and so forth. So it's a refinement of this very initial architecture into the technical details of the solution for this vehicle function. And on the right side here, we have again also logical model, right? That is a detailed model of a micro in this example, so of a semiconductor component. Okay, so it's a view of a typical tier 2, right? So we really here talk about the details of the controller, of the die, of the RAM, of the ROM, and so forth, right? So what we have to manage on one hand is we should be able to build these kind of model refinements, right? On the other hand, we also need to manage the integration of models, right? So the logical model of an MCU will become a part of the higher level technical safety architecture. And the technical safety architecture for this part of our vehicle function or system becomes a part of the overall model of that function. So this integration of models of lower level into the models of a higher level is really something that is crucial for the overall consistency of the safety analysis. Yeah, a few words maybe about the technical core features of Medini Analyze, right? So system architecture and functional behavior modeling in Medini is supported through a modeling language called SysML. That's a standardized systems engineering language, graphical modeling language that we use not only for structure, but we use that also to define the behavior of a system or of a system component or module. And then the connected methods to these models include HAZOP, HARA, PHA, FHA, depending on the industrial domain. So HARA is for automotive, FHA, for example, would be for avionics. We are able to manage operating situations. We are able to manage safety goals or safety objectives. We are able to manage safety requirements in Medini. You can run all kinds of ASIL, ZIL, decomposition. We support DFMEA, PFMEA, SFMEA. Then we support FMEDA in the sense of IE 61548. We support fault tree analysis, both qualitative and quantitative analysis. We do support dependent failure analysis. We support the single point fault and latent fault hardware diagnostic coverage metrics. That's the automotive specific method for analyzing the hardware architecture maturity. We do support failure rate classes. We have a number of so-called failure rate handbooks integrated into Medini, starting from Siemens SN29500, IEC 62380, FIDES, the MIL handbooks, the MIL 217 Plus, the newer version of the MIL standard, as well as IEC 61709. So all of these handbooks are actually part of or can be part of the Medini installation. So no other handbook or whatever paper version of what is required to use them. In addition to these features, we do support the integration with project and version management. Specifically, we support with task management. We do support review assessments. There is support for supply chains. If you remember, the integration of models of a lower abstraction level into a higher level of abstraction, that's directly supported with a feature in Medini. We integrate with version management systems like SVN or Git or something. And we do support integration with PLM or ALM systems here. And we do have a feature to compare arbitrary Medini projects and also to merge the differences that can be found during this comparison into a consistent target version. Very useful for a number of use cases, for example, teamwork or working in teams, right, on the same project. Also useful for creating repositories of functions and features that can be feature-wise merged into an application project. So it's a very useful feature for a number of use cases. There is a lot of support for reuse and automation. So we provide a number of checklist templates, but also the user can define their own checklist templates. The same for project templates. That's to store additional reusable knowledge in templates that can be used by all applications that are based on this project template. We have the ability to create what we call element libraries or libraries of electronic components, for example. And you can generate work products in different formats like MS Office or PDF or HTML. Medini also is highly extensible and customizable, so you can use Java scripting, for example, to really read data from Medini, to also write data into Medini, and to provide a number of additional automations or additional application or environment-specific helping functions. So I have one example for this here. So there was a presentation on our user conference from GM about how to manage functional safety um, execution of complex systems. Basically, in that workflow, GM uses fault trees of the fault tree analysis on SysML models or on system models actually. So they create based on a specific pattern. They create fault trees, and this is done by analyzing the system models and then manually drawing the fault trees according to these models. This process has been automated by GM in order to be able to automatically create these fault trees and to be less error prone there concerning the manual creation of these fault trees. You see that on the left side, that was an earlier manually created fault tree. On the right side, this is the same fault tree which they created based on an extension to Medini in an automated fashion. This goal could be met simply by adding a number of scripts to Medini that use this extensible framework and this open API. In terms of interfaces to other tools or other approaches, other methods, right? There are a couple of interfaces available in Medini. So safety objectives, safety goals, safety requirements can obviously be managed in Medini, but can also interface to tools like JAMA, DOORS Next Generation, PTC Integrity, to mention a few here. So there can be this bidirectional interface can be supported to really have the safety requirements, which are actually created and managed in Medini, to have them also be part of the larger view of requirements in a project or in a certain development. Another interface regards the system models, right? So you are able to create and maintain the system models directly in Medini, but you're also able to interface with system engineering tools. Also here I have mentioned SCADA Architect from ANSYS, but also IBM Rhapsody, Enterprise Architect, MATLAB Simulink. Can also go down to IP design tools or EDA tools like from Cadence, from Synopsys, or also from Optima, to mention a few here. When it comes to FMEAs, you see here there's a little picture of an FMEA table or worksheet, as well as a kind of icon for a failure net. Those, including the structure and so forth, can be exchanged with other FMEA tools based on a standardized exchange format, which is named MSR XML. So that's supported for exchanging between FMEA tools. We do also support the import of fault trees from Fault Tree Plus, from OpenPSA, from Kafka, right? And last but not the least, there is a bidirectional interface with Excel. So Medini is able to read arbitrary data from Excel and also to export data into Excel. Yeah. I forgot one. I forgot one down here. So there is also a component which actually connects Medini to task management environments. If you think of tools like Jira, Redmine, and so forth, Track, then this is actually to interface between Medini and these kind of tools, right? That allows a task-oriented work or task-oriented workflow, where the tasks themselves are managed in the task management system, but can be linked to elements in Medini and can also be viewed and edited inside Medini. Two small examples here for this integration of Medini with other engineering tools. So you see here ZF as an example uses Rhapsody as an engineering tool for the modeling purpose. They are using DOORS to manage requirements, and they use Medini for the safety analysis. And you see here there's an iterative approach basically, and there are heavy use of these interfaces between these different tools. In their case, here is another example from Hala Mechatronics. You see that they also use different tools. They use Rhapsody again for modeling the whole system, right? They use PTC Integrity as a configuration tool and as a task management tool, and they use Medini for the safety-related task. And in their process, it's a highly iterative process. So through this interface or interfaces with these different tools, Medini also supports this kind of highly iterative work style or development style that this custom actually uses. Yeah, and finally, that's again from the same presentation from Audi, right? That's the result after implementing the Analyze into their workflows, right? So they have now an integrated tool set. They have everything in place and traceable. They do not have any more duplications of data or these kind of redundancies, right? Um, they developed links. These are attributes of the models, right? Um, and the advantages there really is to avoid duplicates. There are no updates necessary because everything is being changed based on the traceability. There is a lot of implicit knowledge, of course, specifically because of the relations between the objects that can be visualized, and also the interconnections between elements at these different system analysis or safety analysis work products can also be visualized and maintained. Now let's have a look into the software tool itself. In our little demo here, we want to model an electronic steering lock, a feature in the car for theft protection that basically uses a magnetic coil to push and pull a locking bolt and push and pull it into and out of the steering column, such that the steering actually will be locked during the car is parked. Okay. We also have a controller here which is responsible to execute the commands based on information from outside, including the ignition status, for example, and also the is powered by a 12 volt power supply here. So very basic function in the car, but in terms of safety analysis, actually a very crucial component. We will see this in a second. Okay. So the first thing we would look like are the potential functions of this item. It's called an item, right? I have a number of vehicle functions. I have one function which is, I can show it here, lock steering, and the other function which is called unlock steering, right? So I have these two functions which are mainly which are provided by this little system. Okay, so if we look into one of our task lists or checklists, which we typically use also as a guidance for the user, right? If we would want to create a functional and later on a technical safety concept, right? We first have defined already our draft architecture. We have our item functions created, right? And now we want to understand actually what can go wrong with our two functions. Okay, so we basically would run what is called a HAZOP. Okay, so looking into this, right? So I'm in HAZOP, I'm combining a guide word, it's so-called guide word, with the method itself to identify potential malfunctions, right? So here my guide word is no or not, right? And my function lock steering, and well, this would result in no lock, or it's a little rephrased here into lock not activated when required. Okay. I do have other malfunctions identified here. For example, this one here is interesting maybe. Locks when not required. Yeah. So let's focus on these two malfunctions, and in our workflow, we now might want to create what is called a hazard analysis and risk assessment. So we want to understand what really can go wrong with these malfunctions in typical driving situations. Yeah, so that's my scenario analysis. I'm actually defining what is called a driving situation, right? I look into the location, road conditions, environmental conditions, traffic, people, the use of the item itself. The speed is an interesting parameter, and also additional situation properties that we want to take into account. And I combine each of these driving situations with my malfunction, right? So if I do it, maybe I can do this a little structured here and look into the really critical stuff. So just assume you're on the freeway, you're changing lanes, you are at not very high but high speed, okay? And now the malfunction locks when not required occurs, right? This results in a hazard, steering blocked, um, with the potential effect that you might crash into other vehicles or leaving the road or crash into structures, okay? We rate this with a very high severity, S3. The exposure of the driving situation, changing lanes on the freeway, is E4, so generally happens very often. And the controllability, in fact, is rather low because you might have a very short distance to other vehicles. Based on these parameters, then Medini is eventually calculating the ASIL for this hazardous event, and we are supposed to assign a safety goal to each hazardous event that has an ASIL higher or equal ASIL A. So there are additional elements here. So for example, you have a matrix view that you can use to really understand where all the malfunctions really analyzed with all of the relevant driving situations here that can be configured to the needs. You will have a driving situation catalog in Medini that can be provided by us, or can also be provided by the user himself. That comes with these properties that I referred to, and also comes with a predefined exposure level. For example, here we have an E3 situation, entering or leaving a parking spot, right? The main operation really is just by using drag and drop. So I can go down here at the very end of the table. I can select the driving situation I want to analyze, like this one. Can add the situation here. Can combine the driving situation with the malfunction that I wanted to analyze. For example, unlock no no locks when not required. For example, here, right? We get a new line into our table. I can now start filling this hazardous event. I can say, okay, the steering might be blocked again. Um, we are at very low speed, but we are somewhat in an alley, right? So we could crash into structure. Um, Maybe because of the low speed, it's an S1 E3 that comes from the catalog itself, and we can we can think that maybe this solution is slightly controllable and will end up with another ASIL QM. Right, so that's the Hera component, widely used. You can distribute your Heras into different Hera models. For example, here I actually have two Hera models, one for the lock, one for the unlock function. So that's nicely configurable and also maintainable. So it's not the situation that you have huge tables, but you can distribute the content of these different Heras into different Hera models. Let's follow the ASIL here, which we the safety goal here, which we have defined as prevent activation of steering lock while driving, and it receives an ASIL D rating because it is assigned also to a hazardous event that has an ASIL D as the result of the analysis. Okay, so we can go for this one and see this in another editor. This now is our safety goals and safety requirements editor. You can use this graphical view for these. You can also choose to have a tabular form or tabular editor that is also available. So different notations, different editors for the different elements. Let me quickly open it. Safety goals or safety requirements list editor, and then it has not this graphical form, but it still provides you with the details of the relations of the refinements, and comes then with additional properties that are then defined and shown and presented to the user in this tabular format. Back to the graphical view here, and that's our safety goal: prevent activation of steering lock while driving. We break this down into a highest level functional safety requirement: disable locking function while vehicle is moving. And we have now two additional refinements here. One is detect vehicle state based on speed and ignition, and the other is ensure locking function is inhibited while vehicle state is moving. So what we say is our safety concept in this scenario here is, if we know the vehicle is moving, right, then we will basically cut off all power supply from this magnetic coil. So based on this very generic concept or idea, right, we start at the same time as we refine the safety requirements, we also start to develop what we call a functional safety architecture. That's here. That's again now, it's a refinement of our very initial item architecture, right? We know a little more now. We know that we have our controller. We know that there are a number of technical functions which we assign to the controller. We know that we need to know where the locking bolt actually is positioned. So we add a sensor for this purpose. And also, as a part of our safety concept, we say we actually have two coils. One is to open to pull the locking bolt. The other is to push the locking bolt to close the steering lock. Okay. We start to develop our or to allocate our safety requirements here. For example, our controller here has a number of safety requirements allocated. For example, here detect vehicle state based on speed and ignition, and other function safety requirements are added to this functional block if you want, right? In addition, for each of these functions that we have here as technical functions, we can also start to understand what are the potential malfunctions involved with these technical functions. One example for our evaluate ignition state here, right? We have identified 4 malfunctions which can be seen here in the model browser. One is we have no ignition state information. One is our function reports ignition is on while the ignition actually is off, and the other way around. And we may also have some situation where the result from this function actually is somewhat unstable, right? So sometimes it will return with a correct result, and sometimes it might return with an incorrect result. Each of our malfunctions that we define here, we can now set into relation, right? We can open what we call a failure net, yeah, and you will see here that our no ignition state information as a malfunction might lead into a malfunction of the lock steering function, that is locks when not required, and the other here is it might lead into a malfunction unlocks when not required in our unlock steering function. Both of these then actually result in system or top level hazards or top level effects. I can also see the causes for each of the malfunctions here. These are potential causes, and that really goes down to the root causes, like here production errors or and others, right? This can result into random hardware failures, which are coming into picture right here. And these failure nets actually can be used to illustrate the complete cause-effect chain from the root causes up to the system level hazards and top level effects, right? That's what is called a failure net. If I want, I can also use this instead of failure net. I can also say I want to derive. Here I want to derive an FMEA worksheet, right? That's then a normal FMEA worksheet that you might know from FMEA tools or from Excel, right? That has all the columns for the failures, for the failure causes, for the failure effects, and other columns depending on the FMEA worksheet layout that you have chosen for this particular FMEA exercise. No. Okay, let's go back to our function safety architecture. Maybe I can remove this one. Okay. One other element here, or one other question usually is, how do I actually refine my requirements? So what could be a potential workflow, right? So let me give you one example. We have here what is called a port. That's a connection or a starting point for a connection. It's an output. In this case, for the power supply for my closing coil. Okay. My ports here, as any other element Medini, can have failure modes. For example, here I have a short to power. That's a failure mode, right? Or a potential fault that this port actually can have. We are at functional safety concept level. We just know that there is a power connection. We don't know the details of the technical solution, how this is actually provided. But here I can say, okay, I can have a short to power. A short to power probably would lead to a activation of the closing coil. So I can analyze the situation in, for example, a fault tree. I have that here. Yeah, so I'm creating in this case, a qualitative fault tree to understand potential requirements. So I can say that's my undesired event. Steering wheel gets locked while driving. Okay, this can happen if I start to drive with a locked steering, if there are illegal requests sent to the closing coil, or and this is an OR gate, or if the closing coil was activated without a request. And this will happen if I have a short to power on my closed CMD. I can put this side by side, and becomes a little easier to follow. Yeah, so this event here, short to power, this represents my short to power failure mode. And this short to power failure mode belongs to this close command port that is actually power supply for the closing coil. Yeah? And here I can say, okay, at the function safety level, I can't do much here. I know it's a base event. I know it's an event that leads directly to the undesired event. Okay, but at least I can derive a requirement from this situation, right? That has been done already, and I can jump to that element. And there is a requirement, which I can also put on the diagram here, then I can see that better. A requirement, provide a mechanism to disconnect the power supply for the coils. Yeah, so I can use at the function safety concept level, I can use requirements refinement. I can use fault trees as well as failure nets and FMEAs, as well as HAZOP to analyze my safety approach, my safety concept as such, and will find additional requirements which I'm going to implement in my technical solution. Brings us to the next point. If we follow this requirement here, right, then we can say in this example, this has already been kind of provided in this Medini project. Okay, this requirement is allocated to an element that is called power supply switch. So let's have a look where this power supply switch actually is located. Let me close a few of these diagrams before. Okay, and we have this power supply, don't save, this power supply switch right here. Yeah, so after finishing my functional safety architecture, my functional safety concept, right, I'm now diving into the technical implementation of my electronic steering lock, right? So I'm creating what is called a technical safety architecture and a technical safety concept, right? So I'm now providing technical solutions for each of my requirements that are coming from the functional safety analysis. For example, here I'm saying I'm using CAN for the communication, so I have a CAN transceiver. I'm using a micro. Inside the micro, I will have a 3-layer architecture. I'm using a power supply and an according monitor, and so forth. I also have my connections between my ECU itself and my opening and closing coil that we have seen before. Now, um, at this level, actually, you would start to distinguish between between a hardware safety architecture and a software safety architecture. Okay, so let's have a look into the software safety architecture first. Okay, yeah, we are right here. Okay, so I'm saying I have my software architecture in terms of software modules. The software modules are connected to elements in my technical safety architecture. In particular, they are connected to the ports which provide information or which are supposed to send information, right? I have here two functions in my ASLD layer 2. One function is the end-to-end protection, and the other function here is input validation. Okay, let's look into the details of this end-to-end protection function, which in our case uh, actually is specified using a activities diagram. So I'm saying I have certain inputs, the ignition and the vehicle speed. Um, I'm going to check the CRC. I check the message counter. If all of this is fine, then I can read my message data and actually can send out my message data to this out port, which is called out message here. Of course, it's very simple, simplified and simple, but that's the yeah, the idea of the example to stay at a very simplified level. Each of my actions, basic actions that I have here in this activity, right, can again have potential faults, right? So my check CRC action here may have a fault out of coverage by algorithm or any kind of data fault, right? So remember, this is a software data flow and object flow analysis, right? Again, here I can say I want to derive in FMEA, which then would result into a software FMEA, right? And I would have my software uh, basic actions, my potential failures, and I could start to add also effects and causes, right? So that's a software FMEA, one of the typical analysis methods for software. You can also apply HAZOP, for example, here. You can apply software fault trees, for example. So again, we use the same safety validation methods for the software part here. If we look on the other side in more details into the hardware safety architecture, right, that we will find here, we basically at this point would not use diagrams anymore because number of elements for the hardware safety architecture might be very, very high, right? So we use tables, which is in fact in valid notation for system models in our thinking. So we have components here, like we have maybe we look into the micro, and in the micro we will have this Aurix line right here. Okay, so we have a line for an element called MCU1. That's the first micro in our technical safety architecture. This is of type Aurix, so I can predefine my types somewhere else and reuse them in my application, right? And from this definition of the type itself, we will inherit the prediction mode, which in this case is IEC62380. We will inherit also the failure modes, the failure rate distribution in percent to each of the failure modes, and then according to the raw failure rate and the failure rate, right? With applying scaling expressions, right? We will come then to the failure fraction for each of the failure modes. So this reliability prediction really is based on failure rate handbooks. There are other ways of assigning failure rates. You can have user-defined failure rates if you just want to budget, right? You can have sum of failures if you just want to, if you just know the fit rate for each failure mode, then you can assign. You can also do that, and that all can be done either on the instance level, in this case MCU1, or we can also go back to our type definition, this AURIX definition here, which I can open in my properties view, right? And you see it has a part number. So if I'm importing a BOM, a bill of material, then Medini can match against the part numbers in the library. It has the failure modes specified here, right? In this case, I have only permanent faults, but I could also add transient faults. It has the prediction method predefined here. You can also apply scaling factors down here. So this is all available in the predefined properties of an element type, and it's here just utilized for each of my elements that I have in the BOM. Okay, if I have the BOM then in this sense somewhat set up, I can go ahead and say I want to derive a diagnostic coverage worksheet. That's the hardware DC matrix worksheet, right? In this example, that has already been done, so I can jump to that particular element in my project. Diagnostic coverage DC. Yeah. My cover sheet actually allow me for a number of preset things for my analysis exercise. So I can, for example, say I want to analyze multiple safety goals in the same worksheet. I want or don't want to see ports and their failure modes, right? And then the worksheet looks like this. So it's actually listing up all the components from my bill of material. It would provide me with the failure rate. I can set the safe failure fraction if I have knowledge about that, and it allows me to say it violates or a failure mode violates my safety goal as a single point fault, or violates my safety goal as a latent fault, right? And then I can bring in my safety mechanisms, which again can be predefined, like you see here, in a library that can be shared between application projects, right? And then finally, it will calculate for me the single point fault and the latent fault metrics down here, okay, with the expectations and the actuals. This, by the way, can not only be done for permanent faults, but you can also include the so-called transient faults here, and then it would also calculate the transient fault metric for the single point transient faults and the latent transient faults. Since the last version of Medini, we also have something here that is called SM coverage. That means safety mechanism coverage. So you can decide to play around with the safety mechanisms. You can turn them on and off, assign them to your project, and then the worksheet will tell you with which of the minimal sets of safety mechanisms you can still achieve your target numbers for the metrics. Last but not the least, of course, we still have to calculate the probability of safety goal violations. So what are actual safety goal violations in the sense? We are doing this with fault trees, but this time you will see that the fault trees actually get numbers, right? So each event in my fault tree has a probability and the frequency. I have my undesired event again here. I have my intermediate events down here. I have my base events down here. So for example, here I have a diode, right, that may have a short failure mode, an open failure mode, and a drift failure mode. Each of these the event itself, right, is linked to the failure mode, to the short, to this element dio with this failure mode short. That's why you see this little red dot there. It means it is linked to an element in my model. I have my bidirectional Zener failure. I may have a safety mechanism here, failure detection by online monitoring, again coming with probability and frequency. And this all, based on fault tree algorithms, results in the overall numbers for the fault tree. I can evaluate my fault tree, like here. I can say I want to calculate my cut sets. Cuts are then, of course, shown with probability of each cut set, and also I calculate here the importancy. That means how much is this particular cut set contributing to the overall result of my fault tree. The same down here for the events. I have all my events in the fault tree listed up here, and it tells me also what are the most critical events, right? So this one, failure detection, but this one is a safety mechanism, has a rather high criticality. So that means this would be a candidate for further analysis, right? And so based on the fault trees, based on the DC metrics, based on my software safety analysis and my system safety analysis, I finally can go back to my safety goals, right? Open the safety goals with the list editor, and then you see here I have my safety goal number 2: prevent activation of steering lock while driving. Further definitions here. But here you see I have my single point fault metric and my latent fault metric target achieved. Yes, no, yes, in both cases achieved, right? I have my evidence listed here. I have my PMHF, so the probability of safety goal violation with 2.46 fit, which is below 10 fit for ASLD, and that means also my PMHF target has been achieved. So I'm now somehow done with all the analysis validation activities, and yeah, ready to build my ESL system based on these safety architectures. You have seen that Medini actually keeps all the traceability between different artifacts. So I can navigate from each of these elements to all of the related elements. I can also, if I want, I can also visualize the relations in a view that shows my dependencies. So here I see it's just for the next level. My safety goal depends on a number of hazardous events, but also has relations to safety requirements, to diagnostic coverage worksheets, to events in the fault tree, and so forth. And I can increase the depth, and then I can really provide rather large pictures of how each of my elements is connected to other elements in my project. Yeah, I hope this gives an overview of what Medini can do for you. And yeah, thank you very much for listening in.